Our species probably began about 200,000 years ago, and judging by the fucking state of us, I think we can all agree it was a terrible idea. We are called Homo sapiens, but we were not the first human-like creatures on the planet, however. Homo habilis were making tools about 2 million years ago, Homo heidelbergensis were building shelters about 700,000 years ago, Neanderthals were probably just as brainy as us. They wore jewelry, maybe buried their dead, and always passed the joint to the left. There were at least 15 other human species we know about, and now they are all gone. The last 3 surviving species of human were Neanderthals, who probably died out about 30,000 years ago, Homo floresiensis, who disappeared about 12,000 years ago, and us, Homo sapiens, aka bipedal bastards. And if you hadn't noticed, we are still here. So where be dem other hominids, yo? Neanderthals, for example. Neanderthals were probably stronger than us, a bit taller, with a rather different skull, and a bigger brain. Then why are they gone? You see, old Gary Neanderthal might have been a smarty pants, but we had a secret weapon, which is mouthy word noises. Speech is fine for dissing and cussing, but it lets you do other stuff, like organize. This allows you to, as the evolutionary biologists put it, fuck shit up! Neanderthals were hanging about in Europe doing crochet, cracking open cold ones, until around 45,000 years ago, when us sapiens turned up coming from East Africa. And within 5,000 years of meeting us, they were gone. All of them. Combine that with the fact that we can make big wordy noises, were socially complex, and probably had domesticated doggos at some point for help, and we were a force to be reckoned with. So that was that. We were bumming around for a while as hunter-gatherers, the land was often barren, the climate was often hostile, death lurked everywhere, so Portsmouth, basically. But it really wasn't all bad. We think the average work week might have been around 20 to 40 hours. Their diet was probably quite varied. Vegetables, fruit, nuts, insects, borzoi, whatever they could find. And they weren't idiots. Most members of the tribe had to know the core skills of survival. Which berries will make you dead immediately, how to remember the terrain, how to build tools, how to stay alive. They were generalists. They had to be. Anyway, that went on for a few 100,000 years until we got around to developing agriculture, probably about 12,000 years ago. And suddenly, if we don't find food, we'll all die, turned into, if you eat my food, you'll die, then into, I'm full, but I'll eat some more. And then into, yeah, I'll have the gluten-free macaroon and the lactose-free avocado shake. Merci beaucoup. And then we went off to build society. How? Scrawny, breakable, generally pathetic, but enough about myself. We are not a formidable species physically, but we can do language. And if you can do language, then you can do myths. And if you can do myths, then you can conquer the world. You will own at least hundreds of thousands of objects in your life, because you believe in a myth called money. If you give me this paper and the number is right, I will give you stuff. And the myth works because most of us agree to play by the rules. The same applies to universities, governments, nations, whatever it is. It's not that these things are lies, it's just that they're abstractions that only live in our heads. And if you don't have language, you can't do them. You really can't. And if you can't do them, you can't do big societies. Language is probably the gateway to civilization. And now, we own the fucking world. But it's been quite a journey. There is some evidence that around 100,000 years ago the human species bottlenecked to somewhere between 3,000 and 10,000 humans in the entire world. By definition, that made us an endangered species, teetering on the edge of extinction. One theory holds that this was thanks to a supervolcano in Lake Toba, Indonesia, possibly bringing in a volcanic winter. And even if that wasn't the cause, disease, strife, famine, ignorance, and hardship weren't occasional visitors to the human condition, they were the human condition for most of our history. But here we are now, a most populated planet. For better or worse, we have arrived. It took 200,000 years to get to our first billion humans, that was in 1804, but then we jumped to 2 billion in 1927, and then 3 billion in 1959, 4 billion in 1974, and finally 7 billion in 2007. And now, we are invincible. We've outsmarted time, we've outsmarted death, we've outsmarted the crops and disease and the weather. The state of the human union is strong. What could possibly go wrong now? 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 I met a traveller from an antique land who said 2 vast and trunkless legs of stone stand in the desert. Near them, on the sand, half sunk, a shattered visage lies, whose frown and wrinkled lip and sneer of cold command tell that its sculptor well those passions read, which yet survive, stamped on these lifeless things, the hand that mocked them, and the heart that fed. And on the pedestal these words appear. My name is Homo sapiens, hominid of hominids. Look on my works, ye mighty, and despair. Well, then again. In 1977, a probe was launched into space called Voyager 1. 41 years later, Voyager 1 is travelling away from us at about 38,000 miles an hour and is now 13 billion miles distant. And aboard Voyager is a message from Jimmy Carter, the 39th President of the United States. And the message reads, "This is a present from a small, distant world. A token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours. We hope someday, having solved the problems we face, to join a community of galactic civilizations. This record represents our hope and our determination and our goodwill in a vast and awesome universe." And were we able to include just a few more lines in that message to tell our spacey friends a little more about ourselves and our deep history and our ambitions and our ancestors, just maybe we'd say that, wow, P.S. we think shit went down like this. Life probably began on our planet about 4 billion years ago as simple organic machines. We don't know how yet. Then a sudden explosion of diversity 500 million years ago. 50 million more years and plants are taking the land over. 50 million more and insects have arrived. Next, the dinosaurs are taking the stage, 700 species at least, ruling the planet for around 145 million years before something, possibly asteroid-shaped, wipes them out. But it's okay because here come bats and butterflies, giraffes, bears, hyenas, sloths, vultures, mammoths, turtles! You fucking name it. And then the rise of the primates, and 2 million years ago appear our first true ancestor, Homo habilis, and at least 15 other species of the Homo genus spreading out across the world, until about 200,000 years ago when a new genus, our genus, emerges, Homo sapiens, large-brained organizers, talkers, thinkers, capable of high abstraction, of building tribes and cities and nation-states, capable of ending the world in a day. We have stepped into an age of great technological potency, though there are gaping holes in our wisdom. We've become a global superorganism, though we still harbor our tribal inclinations. We've pulled a bunch of fuck-ups, and we're really quite confused and alone, and frankly scared. But we hope to enjoy the privilege of being a semicolon in history, rather than a full stop. So on behalf of the 150 billion who came before us, and our human cousins who didn't make it, we just hope this message finds you well. And we hope, when you find us, thousands of years from now, that we are well too. In any case, please just write back. It's dark out here, and we're the last humans left.
Mandelbrot's fascination with the visual side of math began when he was a student.
It is only in January '44 that suddenly I fell in love with mathematics, and not mathematics in general, with the geometry in its most concrete, central form. That part of geometry in which mathematics and the eye meet. The professor was talking about algebra, but I began to see in my mind geometric pictures which fitted this algebra. And once you see these pictures, the answers become obvious. So I discovered something which I had no clue before, that I knew how to transform in my mind instantly the formulas into pictures.
It was 1958. The giant American corporation was pioneering a technology that would soon revolutionize the way we all live: the computer. IBM was looking for creative thinkers, nonconformists, even rebels. People like Benoit Mandelbrot.
In fact, they had cornered the market for a certain type of oddball. We never had the slightest feeling of being the establishment.
Mandelbrot's colleagues told the young mathematician about a problem of great concern to the company. IBM engineers were transmitting computer data over phone lines, but sometimes the information was not getting through.
They realized that every so often the lines became extremely noisy. Errors occurred in large numbers. It was indeed an extremely messy situation.
Mandelbrot graphed the noise data, and what he saw surprised him. Regardless of the time scale, the graph looked similar. 1 day, 1 hour, 1 second. It didn't matter. It looked about the same.
It turned out to be self-similar with a vengeance.
Mandelbrot was amazed. The strange pattern reminded him of something that had intrigued him as a young man. A mathematical mystery that dated back nearly 100 years. The mystery of the monsters.
The story really begins in the late 19th century. Mathematicians had written down a formal description of what a curve must be, but within that description there were these other things. Things that satisfied the formal definition of what a curve is, but were so weird that you could never draw them, or you couldn't even imagine drawing them. They were just regarded as monsters or things beyond the realm.
They're not lines. They're nothing like lines. They're not circles. They were like really, really weird.
The German mathematician Georg Cantor created the first of the monsters in 1883.
He just took a straight line and he said, I'm going to break this line into thirds, and the middle third I'm going to erase. So you're left with 2 lines at each end, and now I'm going to take those 2 lines, take out the middle third, and we'll do it again. So he does that over and over again.
Most people would think, well, if I've thrown everything away, eventually there's nothing left. Not the case. There's not just 1 point left. There's not just 2 points left. There's infinitely many points left.
As you zoom in on the Cantor set, the pattern stays the same, much like the noise patterns that Mandelbrot had seen at IBM. Another strange shape was put forward by the Swedish mathematician Helge von Koch.
Koch said, well, you start with an equilateral triangle, one of the classical Euclidean geometric figures, and on each side
I take a piece and I substitute 2 pieces that are now longer than the original piece. And for each of those pieces, I substitute 2 pieces that are each longer than the original piece.
over and over again.
You get the same shape, but now each line has that little triangular bump on it.
And I break it again, and I break it again, and I break it again. And each time I break it, the line gets longer.
Every iteration, every cycle, he's adding on another little triangle.
Imagine iterating that process of adding little bits infinitely many times. What you end up with is something that's infinitely long.
The Koch curve was a paradox. To the eye, the curve appears to be perfectly finite. But mathematically, it is infinite, which means it cannot be measured.
At the time, they called it a pathological curve, because it made no sense according to the way people were thinking about measurement and Euclidean geometry and so on.
But the Koch curve turned out to be crucial to a nagging measurement problem: the length of a coastline. In the 1940s, British scientist Lewis Richardson had observed that there can be great variation between different measurements of a coastline.
It depends on how long your yardstick is, and how much patience you have. If you measure the coastline of Britain with a 1-mile yardstick, you get so many yardsticks, which gives you so many miles. If you measure with a 1-foot yardstick, it turns out that it's longer. And every time you use a shorter yardstick, you get a longer number.
Because you can always find finer indentations.
Mandelbrot saw that the finer and finer indentations in the Koch curve were precisely what was needed to model coastlines.
He wrote a very famous article in Science magazine called How Long is the Coastline of Britain?
A coastline, in geometric terms, said Mandelbrot, is a fractal. And though he knew he couldn't measure its length, he suspected he could measure something else: its roughness. To do that required rethinking one of the basic concepts in math: dimension.
What we would think of as normal geometry, 1 dimension is the straight line, 2 dimensions is, say, the box that has surface area.
And 3 dimensions is a cube. But could something have a dimension somewhere in between, say 2 and 3? Mandelbrot said yes. Fractals do. And the rougher they are, the higher their fractal dimension.
There are all of these technical terms like fractal dimension and self-similarity, but those are the nuts and bolts of the mathematics itself. What that fractal geometry does is give us a way of looking at, in a way that's extremely precise, the world in which we live, in particular the living world.
Mandelbrot's fresh ways of thinking were made possible by his enthusiastic embrace of new technology. Computers made it easy for Mandelbrot to do iteration, the endlessly repeating cycles of calculation that were demanded by the mathematical monsters.
The computer is totally essential. Otherwise, it would have taken a very big, long effort.
Mandelbrot decided to zero in on yet another of the monsters, a problem introduced during World War I by a young French mathematician named Gaston Julia.
Gaston Julia, he was actually looking at what happens when you take a simple equation and you iterate it through a feedback loop. That means you take a number, you plug it into the formula, you get a number out. You take that number back to the beginning and you feed it into the same formula, get another number out, and you keep iterating that over and over again. And the question is, what happens when you iterate it lots of times?
The series of numbers you get is called a set, the Julia set. But working by hand, you could never really know what the complete set looked like.
There were attempts to draw it, doing a bunch of arithmetic by hand and putting a point on graph paper.
You would have to feed it back hundreds, thousands, millions of times. The development of that new kind of mathematics had to wait until fast computers were invented.
At IBM, Mandelbrot did something Julia could never do: use a computer to run the equations millions of times. He then turned the numbers from his Julia sets into points on a graph.
My first step was to just draw mindlessly a large number of Julia sets. Not one picture, hundreds of pictures.
Those images led Mandelbrot to a breakthrough. In 1980, he created an equation of his own, one that combined all of the Julia sets into a single image. When Mandelbrot iterated his equation, he got his own set of numbers. Graphed on a computer, it was a kind of roadmap of all the Julia sets, and quickly became famous as the emblem of fractal geometry. The Mandelbrot set.
It's not easy to describe the Mandelbrot set visually. It looks like a man, it looks like a cat, it looks like a cactus, it looks like a cockroach. It's got little bits and pieces that remind us of almost anything that you can see out in the real world, particularly living things. So it has a character that reminds us of a lot of things, and yet it itself is unique and new.
The Mandelbrot set is real, an absolute thing, no question whatsoever. Any mathematician or any computer scientist or student in a school can study it and describe the same thing. It's a common experience. And so such things that can be magnified forever and have infinite precision do exist, but they're not touchable.
It's a geometrical shape, an icon, if you wish, which somehow embodies as an example a very important aspect of how the world works. Somebody recently actually called this set the thumbprint of God.
With this mysterious image, Mandelbrot was issuing a bold challenge to long-standing ideas about the limits of mathematics.
The blinders came off, and people could see forms that were always there, but formerly were invisible.
The Mandelbrot set was a great example of what you could do in fractal geometry, just as the archetypical example of classical geometry is the circle.
When you zoom in, you see them coming up again, so you see self-similarity. You see, by zooming in, you zoom, 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 you're zooming in, you're zooming in, and pop. Suddenly it seems like you're exactly where you were before, but you're not. It's just that way down there, it has the same kind of structure as way up here, and the sameness can be grokked.
Now we'll begin our serious exploration of the Mandelbrot set. A voyage which, in fact, could last forever and ever, much longer than the lifetime of the universe. I have here the full set, about 6 inches across. Now, if I blow this up, I'll increase the magnification now 13 times, and you see more and more detail is appearing. And the interesting thing is you see mini Mandelbrots, replicas, almost identical, yet perhaps subtly different, of the original set. And I can go on doing this. Here's a magnification of more than 3,000 times. So the original picture, about 6 inches across, is now half a mile across. And no matter how much we magnified it, a million times, a billion times, until the original set was bigger than the entire universe, we would still see new patterns, new images emerging, because the frontier, the M set, is infinitely complex. And when I say infinitely, I really mean that. Most people, when they say infinitely, they mean only rather big. But this is really infinity. What is so remarkable, in fact, astounding, about the Mandelbrot set is that although it's infinitely complex, it's based on incredibly simple principles, unlike almost everything in modern mathematics. In fact, anybody who can add and multiply can understand the principles on which it's based. You don't even have to subtract or divide, still less use logarithms or trigonometrical functions to comprehend how the Mandelbrot set is created. In fact, in principle, it could have been discovered any time in human history, and not merely in 1980. But the problem is this: although it's only based on adding and multiplying, you have to carry out those operations millions, billions of times to create a complete set. And that's why it was not discovered until the era of modern computers.
There's an interesting parallel with the equation that almost everybody is familiar with, the only equation almost everybody is familiar with, E equals mc squared, Albert Einstein's equation that says matter and energy are equivalent to each other. That was a very simple equation with very far-reaching consequences. And the equation for the Mandelbrot set is equally simple. Z equals z squared plus c.
The letters in the Mandelbrot equation stand for numbers, unlike those in Einstein's equation where they stand for physical quantities, mass, velocity, energy. The Mandelbrot numbers are coordinates, positions on the plane, defining the location of a spot. Another difference from Einstein's equation, and a very important one, is this double arrow. It's a kind of a two-way traffic sign. The numbers flow in both directions, constantly feeding back on themselves. This process of going round and round a loop is called iteration. It's rather like a dog chasing its own tail. The output of one operation becomes the input of the other, and so on and on and on. When the Mandelbrot equation is given a number representing a point, and that number is iterated through the equation, one of two things happen. Either the number gets bigger and bigger and shoots off to infinity, or it shrinks to zero. Depending on which happens, the computer then knows where to draw a boundary line. So what we get from this basic iteration is a kind of map dividing this world into two distinct territories. Outside of it are all the numbers that have the freedom of infinity. Inside it, numbers that are prisoners, trapped and doomed to ultimate extinction. Now look what's happening. At the tip of each hair, it splits into two others, and so on. Each is splitting, going on indefinitely. This splitting up, this bifurcation, going off into apparently random directions quite abruptly, is typical of a class of mathematical entities called fractals. The Mandelbrot set is the most famous fractal.
The word fractal means any geometrical structure that has detail on all scales of magnification. No matter how big you make it, you still see extra new details you didn't see before. And the name was actually invented by Mandelbrot himself. He felt he had to have a name for this area he realized he was working in. And so he coined the term fractal because it conveys this feeling of fragmented, broken, fractional, irregular.
A common characteristic of fractal systems is branching. Trees, circulatory systems, and rivers, for example, all display branching fractal patterns.
There are lots of fractal systems within the body. In my work on the heart is actually full of fractals. The most famous example of it is the blood vessels coming into the heart. The coronary circulation is a pattern of a branching network of blood vessels that's typically fractal, where the branching structures look very similar at different scales.
Even snowflakes, known for their dissimilarity from each other, display a fractal pattern internally.
Fractals are shapes which we are extraordinarily used to in, our subconscious, ill-organized life. For example, everybody knows that if you take a map of Britain on a small school globe, you see a very simplified shape. Cornwall is just a kind of triangle, and Wales perhaps a little rectangle. You can't put the details on a small map. If you look at in a larger map, you add more detail. The closer you come, in a certain sense, imagine yourself like somebody coming on a rocket. From far away you see very little, and the closer you come, the more detail you see. If we come very, very close, you begin to see rocks, and finally the idea of coastline disappears, because one doesn't know any longer where is land and where is water. So indeed arose in my mind to put together a geometry based upon many known facts in mathematics, scattered facts in mathematics, many scattered facts in our experience, many scattered facts in the results of what scientists had done of various kinds, all kinds of putting together all these things and using them as bricks, if you will, of a new building, which is a new geometry.
Living creatures seem to be complicated structures produced from simple rules, simple laws of physics and chemistry. And a lot of the structure that you see in living creatures is organic but pattern structure. Leaves on trees, ferns particularly, things like that, have the same feature that the Mandelbrot set has of you look at little pieces of them and they have lots and lots of detail. And in fact the little pieces look very similar sometimes to the whole thing. It's very tempting to compare the way a simple formula produces a complicated Mandelbrot set with the way very tiny things in nature produce complicated organisms. And there are certainly some similarities in that there is the same kind of unfolding of a process. The instructions are there, but not an actual description of the object.